Good morning, Dr. Sunando.
Hello. Hi, Manisha.
Hi. We are just waiting for the participants to join. Just let's wait for a couple of minutes and we'll start.
No problem. Thank you.
Thank you. Thank you.
Good afternoon, dear participants. Welcome to the second keynote session for the day. Jeff Bezos, CEO of Amazon, once said, "We are at the beginning of the golden era of AI. We have only scratched the surface of what's possible." Today's topic is quite interesting, especially for our students working on different innovative projects. The topic for this session is research trends in computer vision. To enlighten us on this, we have with us Dr. Sunando Sengupta, Senior Researcher, Microsoft UK. Now I request our conference chair, Dr. S. Manisha, to introduce the keynote speaker to us.
A very good afternoon, everyone. It is my pleasure to introduce the speaker for the keynote session by Dr. Sunando Sengupta to share his insights on the topic research trends in computer vision. Dr. Sunando is a computer vision researcher in Microsoft's Applied Sciences Group, known as ASG. He did his PhD work in computer vision with Philip Torr at Oxford Brookes University, where he worked on road scene classification and reconstruction. After earning his PhD, Sunando worked in multiple industry sectors. He did motion capture engineering for the entertainment industry and has designed camera-based monitors to track vital signs such as breathing and heart rates in the healthcare field. Most recently, before coming to ASG, he spent 2 years at Intel working on such projects such as sensor fusion for autonomous driving systems and low precision deep learning models to target field programmable gate arrays. His work has been presented at various industrial trade shows. His research interests include semantic scene understanding, 3D scene reconstruction, optimizing vision models for hardware, and vision for healthcare, among others. Thank you so much, Sunando, for accepting our invitation. We are very happy to have you here with us for ICC Ideas 2022 as a keynote speaker. We welcome you, sir. Over to you, sir. You are on mute, Sunando.
Hi, Manisha. Can you see my screen?
Yes.
Okay. I always have a problem with sharing the screen. So hi, thanks a lot for inviting me to present a talk over here at ICC IDS. And I thank you all the participants, the students over there, and also the organizing committee. So I'll be talking as I was introduced, I'll be talking about the recent research trends in computer vision that has actually taken by us by the storm in the last 5 to 10 years. So briefly about, let me go to the next slide. So about me, I think I'm sharing a wrong screen, is it? Or am I sharing a correct screen? Is it one screen or two screen coming up?
It's a presentation view that we are seeing, sir. So we are like
Ah,
having
okay.
two screens.
You are having two screens. That's what I was thinking. It must be like that. Okay, let me reshare again. Hmm. Okay, let me see.
Yeah,
And
now we
this
are seeing on just this one
only one
screen.
screen. Okay, yeah, now is better. Yeah. About me, I started my computer vision thing basically in 2007, 2007, or maybe a little bit earlier when I was doing my master's in Chennai in IT over there. And then there only I met quite a few people probably who are also associated with SSN now. And then I moved over to do my PhD at Oxford Brookes University in Oxford under Professor Phil Torr's lab. And I was working on quite a few challenging problems over there, and that was the first time, first real world uh, problems that I was fortunate to work with in collaboration with the industry and as well as in academia, and got a taste of what are the things that is happening in computer vision recently. So, like, if we, yeah. So like if you see the computer vision, just we take a step back and we see the where the just we don't have to go to too much earlier, like though computer vision has been there for quite some time. Like the earliest we can actually trace back is the Galileo's experiments or Da Vinci's experiments on the binocular vision, the 3D estimation, and all those things. But more recently, in say towards like in the 20th century, in 1960s, where in MIT, it was in Marvin Minsky's lab, and they wanted to have a summer project. And the intention of the summer project was to simulate or reconstruct the part of the visual system. So it was quite an ambitious thing, and like I think over 70 years from now, and we'll still probably have done only a part of it, and it might take a few more decades to do that. And like that was the one of the attempt, like okay, how to understand how the human perceives the outside world. And then it was followed by Mar's seminal work, where he told that like actually we perceive as the real world object from the primal sketch. It's a 2.5D representation. So things moved on, and things moved on like there was a big step change in the 80s and 90s, where some of the problems that we were starting to tackle, like the optical flow, 3D estimation was done quite a lot in the early in the late 80s and the 90s, whereby Zisserman, Phil, Hartley, over there. And then they moved on to say Markov random field, condition random field, graph cuts, image-based pyramids. So there was a big work field of work being done over there. But there was still the problem was that most of the computer vision, which is still there now to some extent, like it used to work in some of the example, some toy example or some specific candidate example, and the wider adoption of the computer vision was not there. So it was kind of still and very much in the academic phase. So we come a little bit closer to time, like to the present time, and in 21st century, like it was a there is a big optimism in computer vision. And here is one of the one scene. We can see the image, the top image, and if we give this top image to any particular person, and he can tell that okay, there is a person over there, he's cleaning the road, this is the outdoor scene, there are some traffic signs over there, and that means no entry, so the cars cannot go over there, but probably they can come over there. There are other cars towards the left, there's a building. But this scene understanding problem, if you have to give to a computer, or for a computer to understand, like articulate whatever I told, that becomes like we have to then break down the problem into many problems. And this problem will be like given a camera. First of all, there will be a depth estimation. So the things that are far away, like the car is far away and the person is closer, the tree is closer over there. And then there will be like the object recognition over there, like which part is the tree, which part is building, the recognition and segmentation will be there. There is a person, there will be an action recognition that the person is actually on the road and he's cleaning the road. And there are other aspect of the task, like say detection, where we need to find out where are the traffic signs. There will be also the recognition, what are the traffic signs over there. So all of these come whole together, and then we get to the say the problem of say the scene understanding over there. So computer vision, what has now become, it has become a, a set of smaller tasks, but as a sum of all these tasks, it makes a certain application ready. So and why it is important. So it has been like it was always there, okay, we can do like what if we can if we can see and understand a particular scene, and if we can make a computer to do that, then perhaps we can achieve quite a lot. And and we know that our the visual perception is one of the most important sensory is a important sense in compared to the other sensory features that we have. So, and there's a numerous applications. So these application can be from robotics, entertainment, engineering, medical, and we can name on and on. So for example, in the self-driving car scenario, say on the top, there is an outdoor scene. I have to tell, okay, what are the where are the car is, where is the road marking, where is the car, where is the lamp post, where are the people over there, how many cars are there. And similarly, it can also we have similar problems say on engineering side, where say in a factory there are the big these big robots like this kuka arms are there, and they have to grasp an object, and then these object will be taken from one from one place to another place. So that's the engineering aspect. So the robot for manipulation. There are also applications like the humanoids, like how can we make a robot or make a humanoid which has as close facial expression as a real human being. So we have to track all the facial muscle when we smile. We have to track all the small movements over there. And then there is the assistive vision for healthcare, like computer vision can be used for medical image analysis, say like analysis of the X-ray images or the MRI images over there. It can be used for the healthcare system, like for elderly care, or something, or even remote monitoring for heart rate, breathing rate, kind of stuff. And finally, there is a big entertainment industry also, which is like which uses computer vision for from quite some time, like all these animation movies that happen, like, and the realistic animation that are actually driven by human action, and how to like how to bridge the technological gap over there. So these have been like these applications have shown that computer vision has been is being accepted across our daily life. And also there is still always an aim, like how to produce semantically consistent scene from given this visual input. So essentially, this problem is quite a hard problem. So, and like why it is a hard problem? Because the way an image is formed. So when we see like way an image is formed, the image, there will be there is a scene. There are many objects which are lying across the scene. The scene can be of different geometry, and most of the time we can take in a different we can see from a different viewpoint, so that will alter the geometry. And then there will be variation among in the object level. So there might be large number of small object, there can be a large object, but one big object. There will be individual object orientation. There will be an occlusion, like I close my with my hands, I close my face, so they can't see my face. So these are the self occlusion. There is a depth problem. Then the object appearance, they might differ. The object surface properties, which will have a different characteristics in a different environment. Illumination, there will be shadows. So all of them together make this problem a very hard problem. And then we have to compound that. Okay, given the scene, what will be the possible action to to solve the task? So that then it becomes even harder. Like in that image, like if there is a no entry sign, I can understand there is a no entry sign, but that means that I cannot go over there. So there is a possible the subsequent action that has to be taken, or subsequent inaction that has to be taken. So these things make it essentially a harder problem, and that's why it had been over, like for a considerable amount of time, it was always in the academia, or it had a slow adoption. if we say so, for the next slide, this is an image from the Gartner's hype cycle, and we can see them. So there they had many machine learning and AI related subfields, and computer vision was actually over here. Like there was like a huge expectation, and then it actually came in. This is a trough of disillusionment. Like, okay, the computer vision, there was so much of expectation that it can do and solve so many problems, but like, where is it now? And like, this is in 2019, and like it tells that like it is 2 to 5 years towards maturity, and probably it is a little bit more than that. But like, what has happened? Like now we say we take 2 years from 2019, and is as of July 2021. Again, the same Gartner's hype cycle, and we can see like slowly computer vision is actually moving into like a slope of enlightenment, where we are actually now seeing that okay, things are what the field and the industry and the research area, the researchers, they have understood. Okay, these were the actual the coming from the hype and facing the real world problem. These were the actual problem, and now we are starting to make slow progress over there to make actually vision impacting the daily life over there. And I quite believe they may, now there won't be, there's not a big bang announcement like say autonomous driving or something, but what will happen is that slowly in small tasks, computer vision will take it over, and it will have a seamless integration. And this is actually witnessed also in all the research conferences. So this is typical the number of submissions. The blue chart is the number of sub papers that have been submitted in CVPR. CVPR is one of the top conference for computer vision, and similarly, the green is the number of accepted papers. And if you see, like when I was doing my PhD, it was like around 1500, 1700 used to be the general trend for number of submissions. And the other the top conferences, the ICCV, NIPS, there were like few hundreds over there. And then it like in last 5 to 10 years, it has shot. And as of now, in 2022 CVPR, there were around more than 8,000 papers submitted, and I think 8,000 or 9,000, and like similarly around 2,000 or 1,600 papers getting accepted. Some figures around like that figures. So we can see like amount of excitement and amount of the researchers that are being working over here. It's a huge and tremendous. And so when the things happen like that, you get more and more ideas, you get more and more avenues to work, and also discover more and more new problems. So what happened? Like, why there was a big boom in the last 5 to 10 years? So there were like a few things that happened simultaneously. So one thing was happened, like, though it is not that they have not been happening for, but they have been happening for quite some time. But like this is like one of the thing was like, okay, we have a image or image or a sensory input, and like then we pass it through a set of layer of processing units, and which was the traditionally the neural network. Now it's called the deep learning over there. And so that kind of approach proved to be very effective, but it was not alone, because this approach was there before. So what happened also was that there was a availability, because these kind of deep learning based approaches, like they need a huge amount of data, and the reason is that there's a large number of parameters to be tuned. Like we can contrast this with a feature-based approach, where we handcraft the features like hog or safe, or then pass into a SVM-based classifier. So there the feature engineering was more important at and the researcher and only probably a few of the computer vision PhDs and the postdocs or the masters, they will be able to do those feature engineering and then do a classifier. But what changed was that, okay, we make a very simple feature and simple like cascaded like processing layers and let the feature engineering be done by that system itself. So what happened that, like, because of this large number of parameters, we need now a large amount of data. And so there was an previously um, like most of many of them, the standard, like in the late 2010s, like late to 2000s, like 2007 8, the one of the standard in computer vision data set was the Pascal visual object challenge data set, the Pascal walk challenge. And over there the number of images was around 10,000, in tens of thousands. And like then came this data set from Fei Li's labs in Stanford, where like they have been curating the data set, all the PhD and the students and the mechanical turks that were used, and they created a data set for more than 1 million images with over 1,000 categories over there. And that actually like helped, like, okay, there was an availability of a huge data set to train these model intensive these parameter intensive models. And similarly, there were others. There have been other data sets like the COCO, Kinetics, which has for action recognition, object detection, segmentation, like that. And the third thing that was important was like there was the availability of the hardware that can actually be used for training and inference. Because if we have to do because this deep learning based system, like they are powered by the, like, we have to do small computation, simple computation over but a lot of them. So the GPUs were perfect match for them, and the GPUs also had matured. There was a software tool chain which had matured. So all of these three came together around in 2012 over there. And then there was this student from Hinton's lab, and he decided, okay, he created the code, and he shared the code. So there was, like, coupled with these three, there was a strong sense of sharing the code, sharing the data, sharing the paper in the community. And that actually helped to democratize the computer vision and lead to so much of breakthrough. So this is the first, the ImageNet classification challenge, the large scale images challenges. And so we can see what happened, how actually the field has changed. Like this was prior to 2012, like all these this green bar is like the post the pre deep learning methods, where most of the methods were based on, say, the discriminant part based model, or something like that. And then in 2012, and most of the time previously to 2012, the amount of changes, like accuracy improvement year on year, they were like minimal, like 1 or 2%, like that. So in 2012, like this AlexNet came from Hinton's lab, and suddenly the error dropped by 10%. And that's a massive drop over there, because we have to see this is a 1,000 category problem with a million images. So there are like number of like for a million image, and some of the images are very hard to find, like telling a difference between different varieties of the dogs, like Siberian Husky and some other furry dog. It's quite hard even for humans over there. And like in 2012, it was met with a little bit of apprehension from the other community. And it was that, okay, maybe we can still win, the traditional methods can still win, SVMs can still win. And then came in 2013 again, there was another 5% drop in the error rate. And then it was like more or less established that, okay, this is going to stay. And we can see how it has for the classification problem, how these deep networks have actually beaten human, like the human error in the data set. This data set was actually curated and labeled by a bunch of bunch of humans using mechanical Turk system. And there also the error was there were around 5%, but like the already the deep learning system was beating them. over there. And like, but however, like you can tell that, okay, this is just a classification problem, image classification, where I have to tell what is the top 5 objects over there, and we have to match within the ground truth labels. So what about the other problem? So then we let's say we saw the similar trends in detection. So you can see like the detection for the first 2 bar, they were all the discriminative part-based model, or a variation of that, and that's a pre-deep learning method over there. And like, so the detection was deep learning was adopted over here a couple of years later, and we can see the amount of jump over here, like this from 2008 till 2014, we were around 21% to 33%. It was improvement, and then in 1 year it was from 32 to 33 to 58, and then the improvement actually jumped like that. So we, and these data sets are so the orange the yellow one, they are the walk challenge walk data set, and this is the coco data set. And the coco data set is quite a big data set over there. So getting a good result on those kind of data set, it's like it shows that this method has these methods have their own have a good benefit to be used. So this was like detection. And then like, so what happened that this broke the kind of floodgates that okay, we can probably use in many like different vision tasks. And if we can use these academic tasks like the object detection, classification, how about we use in actual industrial usage, like the say entertainment, like the motion capture, like animation? Can we use in healthcare? Can we use in engineering, agriculture, transport, consumer devices over there? So there was a big adoption of this in the industry, and like, so for the industry, they slowly what they take a system from the top working system from the academia, and then they tune it to their own problem. Because for industry, it has to work 100% of the time. It cannot work say 90% of the time. We have 90% of accuracy, and it works. It cannot work like that. So no, so and I will talk with some of these industry where I actually have worked, and how these things are being used in the current current applications. So one of them is like the motion capture, which is motion capture for which is used in entertainment, movies, sports, healthcare, and across the board. So over here, this is like this is a typical set where an actor, this is Andy Serkis, and more probably Planet of Apes recording shooting, and like the actor has be he is put markers on the face, and what is need to do is that we have to accurately track these markers. No, sorry. Yep. So we have to accurately track this marker so that you can get the micro motion of your face. And once you get the micro motion of your face, then you can actually do the mesh generation. You can do the retargeting of a particular animated character. So this is like this kind of helmet which from Vicon, and there's like the corresponding output that is being used to read to target an animation. So what happens, animated character? So what happens when we speak? Our muscles in the face changes. So that has to be reflected into the animated character. Otherwise, it will not look realistic. It will look like a cartoon. So that is a small difference. And this tracking has to be done with a high accuracy, like sub-millimeter accuracy. Otherwise, the human eye will able to tell in a big full HD or ultra HD 4K definition movie. We will be able to tell what is anything wrong is happening over there. And similarly, this image is like a shooting set on of Mandalorian, and like you can see like how what they most of the previous production system used to be like you shoot the characters and then they put in the 3D world or another world over there. But over here, the characters were present in the scene, and there was a big video wall which actually runs the and changes the scene over there. So what happens that like the production time reduces, and you can do much more like you can do many complicated actions, but the problem is that you have to track the system, track the characters which are acting over there, and as well as do a very synchronized thing on the background, so that there is no the things doesn't look bad, or there is no uncanny valley over there. And like this motion capture is used also in industry. It is used in healthcare, for example. Like say somebody had an accident, and then how he is walking, you can actually attach the marker to the person's leg, and as he walks, you can do the gait analysis over there. And similarly, in the industry, how it is used, like say you are being in a virtual environment, say an oil rig or something, and you are interacting with the oil rig, but everything is virtual. So it's a some training over there. So you have to you the person is being tracked, and he's being tracked and placed inside a virtual environment. So over there also, this motion capture plays a big role over there. So this is the motion capture industry over there. Then there is a say vision for healthcare, and this is like where you can we use camera based system to find out the heart rate and breathing rate, or any other vital signs over there. And like this particular thing which actually I'd worked, and they over here, like what it is being attempted is like it is being attempted to get how get to a reliable and robust heart rate and breathing rate just from a consumer grade camera. And these are very hard problem, because this has to work in across all the scenes, across all the setup. It can be a dark room, it can have a very bright room, there can be sunlight, there will be windows, there will be objects outside the window, and you have to compensate for that. And moment we the vision has to work for healthcare. It has to work very reliably. So it cannot be like as I told, say 90% of the time, because say if it is work 90%, what happens, like 10 out of 100 where they will be misdiagnosed, or something wrong might happen, and that's very high risk. We cannot afford to do that. And say the same for autonomous system, like an autonomous system which is like it can be autonomous cars, it can be just an autonomous system in a closed environment or a secured environment, where the system actually has to sense what objects are there. So in this scenario, it is a car which is trying to sense the lidar. Via its lidar, it tries to sense what are the object, what are the obstacle, what is an obstacle to it, which an obstacle like a speed bump is not an obstacle, but a little child, that is an obstacle. So you have to like they might be of very small height or something different, but we have to understand that there is a big difference between them. And similarly, like so we have to tell like whether what is the part of the road which is navigable, it can be gone over there, and what are the things on the road. So these are the cars, and the cars can come towards you. And and these like the autonomous system and the engineering is like it's quite a hard problem, because first of all, it has to run for most of the different countries. You can tune them, but like it has to work on different weather, it has to work in day, it has to work in night, and it has to work at a high speed. So for example, like if we till now till recently, like in Europe, in Germany, the roads didn't have a speed limit. Some of the roads have, so you can drive at 200 kilometers an hour. And then for a system to do an say obstacle detection, or do an inference, you don't have much time to respond, because like and at such a high speed, like if you take even a few tenths of millisecond, probably by the time you have taken the image and you have responded, the car has moved ahead. And so there's a chances of like any misjudgment or any miscalculation, the error is the can be catastrophic. So it is very important that like over there, the things are extremely robust and they work extremely reliably over there. We cannot use a car if it is like 1 month of a year, it is always broken down. We can tolerate 1 day broken down, but not 1 month. So the accuracy needs to go in that high level. And the same thing about industry, like now vision as being actually is being used for like being adopted in the industry 4.0, where like there is a specific problems in for each of the industrial sector. I remember one of the trade show I had gone over there, and like there was a food processing company, and this food processing company told that like they have a conveyor belt and they want to track the food, track a particular item of this food that is being packaged to the weighing area, and make sure that things are consistent, quality is consistent. So that is a very different problem. And but on the other hand, there was another problem for like a grasping or autonomous vehicle manufacturing thing. So these are like, and everywhere these are the very specific application of computer vision, which is like where the data set and everything is like very specific. It's not general thing, but like now vision is getting adopted over there. Like one example was that like most of these big factories, they have a safety system. There's a safety mat over there. So when these big machines are going on, like if a person stands on a safety mat, the entire machine stops over there. And like this has to like they like if you have to use computer vision, like you can allow say a maintenance person who is well known how to train the system. He should be allowed to work near the system, but not any other person. So but like the safety mat cannot do that. He can just tell, okay, there's a person. So often they have to do is they have to override the entire safety system to do the maintenance. So those things, like, and these are like a very these are say a recognition problem. I have to detect and I have to recognize the person who is allowed, and he should be to go in. So these are the like if we boil down to all these industrial tasks, these are the computer vision tasks which we want to solve. And we can actually the vision has a capability to solve it, given a set of system and set of hardwares over there. And finally, like one thing is like now, especially in this the pandemic world and the post pandemic world, we have seen how the communication has become very important, and like working towards a better communication. And it is like extremely important to break down the barriers of the distance, like where I can talk, I can when I speak, I do in a where where the means of communication of this video of the video makes it much more personal, where I can actually look properly. I look irrespective of the lighting condition and everything. I look the true self. It's not that I'm looking better or worse, but I'm looking what I should look over there. And like whether I am doing a good communication, good eye contact, and all those. So those things have also become quite important in this world. And especially it will become more and more important, and how vision and AI will be used in these cameras in the next few years. So now, like all these nice things about like it solves the world problem, but there are challenges, and the challenges like one of the big challenges, and each of these challenges represent a research opportunity, and and there is a research trend that is going for each of these challenges like that. So like for one of these is like there has been an explosion in complexity of the models. So this is like one of the again an ImageNet and a ImageNet classification analysis, and how different this is a top one accuracy, and how different methods have improved the top one accuracy over there. And now with all these methods, there is also a chart of what is the number of well, not parameter, but the gigaflops operations it takes per image to do the task, to do the classification task. So if AlexNet was over here, like the VGGNet, which actually which won in 2014, this is way bigger in number of operations over there. But again, like these big networks, and then the ResNet, which again when it was a smaller operation. But as we go, as we see, there is like more and more, these models are getting more and more bigger. And this bigger model, when it's a bigger model, it has its own challenges over there. We can theoretically we can have a huge model like which will solve the one of the toughest thing, but how can we train those big models over there? So like these large model pose their own challenge. So for example, it is more or less seen that it generally improves performance, but not, it's not always the case. But what is the results is that it results in a larger training time, because I have to simply I have to train a large number of parameters over there. And to train large number of parameters, I need a large number of data. And there is a huge requirement of the data over there. Like can we when there is a large requirement of data, the ground truth labeling is becomes expensive. And this what can we do over there? What can we learn with a smaller number of data? Or the labeling might be noisy. There will be we cannot ensure that a million images have been labeled exactly correctly, because there will, after all, the labels are done by human, and there is a human error and human bias involved over there. And also there's another part which becomes important, is the larger model results in larger inference time, so the deployment becomes critical. So, and again, taking back to that the car example, if the car is running at 200 km an hour, I cannot have uh, a model that takes like few seconds to infer one image, so it will be just useless over there. So so all of them together results in there is a increasing cost to train the model, there is a cost to deploy the model, and at the end, for a solution to be practical, to solve the hard real world problem, it has to be even if the cost of training is fine, it has to be efficient in deployment at least. So these are quite critical. So so one of the trends that's happening is that how can we drive the model efficiency? And so there have been different works on to make the model smarter. Like you can have generally there is a it's loosely based, like the number of floating point operations in this curve, which is loosely based to the number of the params. And we can see all these different methods with the accuracy and accuracy of the model and total number of million parameters. And these are different architectures from NASNet, ResNext, Inception, and these are the efficient net. And the main thing is that can we create a smarter architecture which is which will lead to a smaller number of flops, G flops, are the smaller number of parameters, but it's able to learn the same thing. So that is one of the quite an a good and important work, that is a stream of work that is happening and getting to a newer and newer architectures. And not only newer and newer architectures, like newer and newer training mechanism, newer and newer losses, which can actually is the stronger loss functions, which can actually train even a smaller model with a sufficient accuracy over there. So that is one part of which has been active research is going on. But another thing is that often what we see that reduction in the flops doesn't mean that a model will be will run faster in actual hardware. And that is so we can, if we go to the previous slide, like if we see the curve of accuracy versus flops over there, this is much more steeper. While if we take this one, while accuracy versus runtime, it is much more gradual. And over here comes the play of the hardware. So hardware has to, because many of the time, some of the model layers are very much tuned to the hardware. The hardware is optimized for that. So, especially in these kind of GPU based like inferences and like GPU based system, where a simple block of say convolution and a simple blocks without like any sophistication being done, probably a simple larger block will execute in the same or faster time than a smaller but much more complicated calculation that has to be made, because that has become very custom over there. So it has to, the hardware plays a very big role on in actual determining what is the speed in which it finally runs. And as the hardwares are evolving, like they are evolving massively year on year, and things are getting, like there are new things are coming up, and new toolkits are coming up, and they are improving and pushing the boundaries on which what model can run, what are the things like, and how fast it can run. So there was this was a work by Google in a few years back, and like about finding uh, finding a architecture that can be that can be like doing a good for a particular say classification task, but also achieve a good runtime. So what happened, what the hypothesis was that, like most of these the CNN based architectures, like they have like you can see, we can see them as a set of blocks are being processed, and each of these blocks contain certain layers over there. The layers can be like then, and these layers can have different kind of operation. These operations can be say convolution operation, like convolution deconvolution operation. Like each the convolutions can we have a different kernel size, say 5 cross 5, 3 cross 3, 7 cross 7. There will be a skip squeeze excite ratio, different skip operations like identity pool, what is the number of filter size, what are the number of the blocks. So, and can we the idea was that, can we iterate over this search space and find out an optimal model, if not the best model, a model which is quite close to an optimal, and find out like in a reinforcement learning framework where there is a reward for each time I get performance improvements in actual runtime. And then they found out like they can actually find a much more like a reasonably faster model and a reasonably like accurate model by doing this architecture search. Now, the problem with this, the architecture search was that often the architecture search is expensive, because if we can imagine, like if I have to train one network of time, now I have to train a set of networks where each of these networks have their own different architectures over there. So like, and the search space just explodes very soon. And with explosion of the search space, explosion of the training time is there. So, and also the hardware requirement was there. So often like this can be done probably only in some clusters over there. But what can happen, like instead of doing a full-blown search, a human in the loop can be much more effective. Like if a person can like by training and observing, okay, which are the things that are quite important or critical, which of the layers are critical, then you try to like devise a method or a system which can actually tune that sub part instead of doing the whole graph. And then the gains are much better, relative gains are much better than doing the whole model architecture search over there. So this is like one area of a neural architecture search that is being quite an active area of work as of a few years from now. And there are other approaches also, like to reduce the model complexity. Like they can we have one thing is that, like we have, like there is a big network, and say this big network, can it be used as a guide for guide for training a smaller network. So what happens that it's a kind of, it's known as a knowledge distillation, and in a student teacher training format, where we have the teacher model, which is a very accomplished model, basically a complicated and a known state of the art model. And then there is a student model, which is actually a smaller model, a smaller version of it. And what we try to do is that the knowledge that is being there in the teacher model, can it be instilled into the student model? The problem over here is a little bit tricky, and where the way it works is that you have this teacher model and the student model, they have the individual loss function, and there is another loss function which tells that what is the difference between the output of the teacher and the output of the student. Now the problem is that, do you want to compare the loss at the output, or do you want to compare the loss at the intermediate levels? And this is the research things, on what are the good, what is a good semantic point in the network which can be compared like that. So and there is a big field of work especially happening, and this happens, this is very much relevant to the language models, where actually the models are quite big, like they are close to in GBs of parameters over there. So it's like quite large models over there. The another thing which is actually also quite interesting, and work is going on actively, is how about model sparsity? Like, do we need all these are all these the layers, or the parameters of the model, are all of them needed over there? So over here in an example of say a dense multi-layer perceptron, where each of these layers have a set of connections to the next layer, and so there is a weight matrix over there. And if we just plot the weight, probably many of these weights will be zero. So if a particular connection, if a particular connection over here is zero, and then means that if I do a forward pass, this is not even activated, or if it is close to zero. So can it be simplified by removing those connections which are close to zero or zero over there? So this is this is basically using the sparsity, inherent sparsity in the model, and how to use them in a better way. And there are some work and tool chains that are being used for sparsity, exploiting the sparsity and getting the model, reducing the model flops, the model parameters, and also the model flops over the floating point operation for per inference. But again, these thing has to be taken in the context, like actually when it runs on the hardware, there might the flop reduction might not be as might not be as representative as the reduction in the or the efficiency gains in the runtime, and that is always there. And finally, the final challenge we have in this system is about the data. And the data was in early 2000, when the PhD students used to in across all the labs across the world, the PhD students or the master students used to do their own data curation, data set labeling, and all those. And the slowly it became okay, we don't have enough students to label the data, so we have to give it to the profession, or use professional tools Amazon MTurks to get the data labeled, and get other people also, non-academic people also, to get labeled. And the more the vision is being used across the industry, and especially with their specific problems, the data requirement becomes much more harder, because they're a food processing industry with a totally different image set, will have a totally different data requirement than a generic general purpose object detection over there. So on the top over here is this is the COCO data set, and these are the segmentations overlap segmentation over there, like, and there are many and you can see like how this data set labeling is quite an issue and quite a tricky problem. Like over here, like in this image, there is a small person on the over here, and like these labeling one image will take quite a lot of time. And if you have to do millions of the images and for the different things, then it will become even harder over there. And also, like say for example, if you have to say label um, um, medical images over there, you need somebody of a very well of the same background to label it over there. So it becomes even harder to get a good and clean label data. And we know if the data is noisy, probably your system is actually learning the noise also. Though some of the noise is bad, is good, it induces system robustness, but in general, it has to be reasonably clean data. Okay. So now, like, can we use like now, what is the alternative to using these data over there? Like, can we use synthetics? Can we use the synthetic data to train the system and then apply on real world data? So like one of the first earlier use of the synthetic data was by using the Grand Theft Autos the same all the images over there. We know this is like because these images are actually the ground truth is there, like all the planes, the rectangles and everything is well known in advance, and we know which part is the car. So all the game simulation, all the game engines that actually generate the data, and you can actually use those images and also generate the ground truth over there. You can generate the depth over there. So can we use, this was one of the very earliest use of synthetic data for image classification, and it showed actually quite a good result. And now things have actually like all the big companies are trying to build work with the academics to build this a synthetic pipeline which can generate the data. And there is also the data set from the 3D objects there, which can be used in the real world. Like there are some optical flow data sets where actually one of the first pioneering optical flow, the complicated optical flow data set is a Sintel data set, which is actually a movie, is an animated movie. So you can, and we know all the depths, all the flow fields over there. And similarly, like flying chairs from those kind of data set where the 3D objects are being put in a 2D image over there. And there are other 3D object data sets are there, and can we use that kind of synthetics to improve our system, or to just train the fully our system, which will help us or enable us to get rid of this big data problem, because that is a big elephant in the room, and we need to address that issue over there. So like this is a big thing that is happening, and it's aiding the deep learning community also. And finally, I will like touch upon one thing. There is the impact of of these machine learning models over there. And this is a simple chart. Like if we standardize like how much amount of CO2 is produced in the 1,000 pounds of CO2 produced, like average an air travel from New York to San Francisco produces this much. This average human life, though it varies, a person in the developed world consumes much more produces much more carbon dioxide than in the other countries over there. Average American life is average 1 year is this one. A car can run for its whole lifetime, including the manufacturing cost, till the all the cost of petrol and everything. It takes around this much. And the final one is training a BERT transformer model with neural architecture search. So we can say that it's like if it is if training a model with the amount of the GPU resources and amount of the electricity that it burns is so much with the neural architecture search though. So it's not that just training. So we are hitting we're hitting a problem of environmental issues, and that will come soon. And along this environmental issue, there are other issues like what are the ethical issues of computer vision? Like, is the computer vision working equally and nicely for all the set of people that are being represented over there? Are they represented correctly, or there is a huge bias in the data set where the Western world say, or they say a certain group of people are being represented much more and certain group of persons are excluded? So we don't want a system which will work better on say a particular a particular people type or a particular origin. We wanted to the things have to work equally with all the people across the people, so nobody should be left out. There has to be inclusion over there. So this is like the things that is like and these are the problems. They are good problems to have, because that means that the system is getting matured, and it is maturing to the fact that we are hitting these problems, that we have to take care of take care of including all the peoples, and everybody should be benefiting from the advances in computer vision. So finally, I will conclude my talk now. I think there is the goal is that the main take is that the computer vision has been never been so much excitement in the field over there. There is excitement in researchers, excitement in academia, excitement in industry, and I think and this excitement is coming because the things are actually starting to work, or things are starting to work in a small scale. And the moment what is happening is that there is like all the small dots are being connected, and then the bigger picture is slowly emerging. So all the small tasks are getting built together, accomplished together to get a big task being done. And now and the challenge now is to solve the real world end user problem, the make the system robust, make it work close to 100% for most of the expected use case over there. And like this has to be within and it has to address within the desired performance envelope, the accuracy envelope, the hardware envelope, the runtime envelope, and all of them have to run over there. And finally, the data requirement, the environment and ethical concerns, the computer vision is slowly like awakening to this and trying to solve them. And these are the few things that will come become more and more important as it goes to the wider community and the wider world. Okay, now I think so here is my talk, and I thank you for listening. I hope I didn't speak too much, but yeah, so I'm open to questions.
Participants, you can either put your questions in the chat box, or you are free to unmute yourself and ask.
Yeah, I think I should answer the first question. I'm sorry, I didn't see the question before. So, does scene understanding means only understanding the objects involved, or it is also confirm information about the environment? I think it is information about the environment plus the objects, because the objects which are involved definitely have some information in there, because a tree or a car present in the scene has information. But also there is an implication of something like which is not there or which cannot be there, because there are some certain things result in some rules, like a traffic light of a traffic light or red traffic light creates a rule, so a rule over there that no car, I cannot go over there. So there are some implicit information that are associated with these objects in the scene.
Thank you, Sunando, for the answer. Participants, you can unmute or you can just post the questions in the chat box. I just have one more question. So, as most of the participants here are students, if they are new to computer vision, what would you say suggest as the starting point?
Okay, I think nowadays the good thing about with the students is that they have so much of information available. So I will tell that, like, if it's a very new thing and you want to you want to get used to the field, probably it will be good to see some lectures, like most of these conferences, top conferences, they have these tutorial sessions, and this tutorial session, there are some very good lectures out there, and they can from Hinton to like all the big shots of the field, the fathers of computer vision, Jan LeCun and all those things, they can actually listen to those people and their talks over there. And like many of these talks are in a very introductory level, and that will give the interest, like what can be done over there. The second thing can be done is that, like, given after listening to trying out some example, there are so many examples available in GitHub and all those. Like, there has been a true democratization of vision, like everybody can, the bar to start working is actually low now, because the things we just you open Python and then like import a package, and then we are done within a few lines. So they can start with that, and once they start with that, then they start asking some question. Okay, what else can be done, what else can be done, and what if this image, I try another image or try another problem. And in that way, like, once the interest is there, like I'm sure like the students will find their own way, because these students are very smart.
Sir, I do have a question. It's related to the last graph that you showed. Is this transformer models, as much as they perform so well for different applications, they always come with the overhead of, computation time. So is there any way we can address this issue, or like we can kind of, are we moving towards a solution
Yes,
to this issue?
so there is actually movement happening, especially in these transformer-based models over there. Like in speech, so in natural language translation, there is the one of the techniques that I mentioned before, the knowledge distillation, that is being worked quite a lot, where we have a very big transformer model or very big model, which is the teacher model, and there is a smaller student model, efficient model, and that the knowledge is being distilled from the bigger model to the smaller model. So there are quite a few work like that because at the end, where these kind of especially these models are used, say auto completion, the language translation, linear, like real-time language translation over there, or captioning, like say we are trying to write a mail, and then the auto complete feature. So those things, like what happened, they actually run a much more optimized version of the model. And this optimization starts with like you start with a big model, and slowly you reduce it. And it's not only one technique, you have to use all the techniques together. You have to use, say the technique has to be used, say sparsity, we have to use the distillation, we have to use also the neural architecture search to find out what is the best way. So over there, probably the best thing is that starting with not the very expensive and the complicated and the good model, but start with a slightly more efficient. Like there will be a Pareto curve where like we find the optimal efficient model versus the accuracy, and we start with that, and then pull it more towards like smaller model but still accuracy. And there's a very active research being going on over here.
Thank you, sir. Thank you very much. So Thank you, students. Thank you, participants. Thank you, sir. If there are no questions, yeah, I think there are no more questions. So thank you, Dr. Sunando, for such a wonderful session. Be it the details of the timeline of computer vision or the real world applications of computer vision in the field of entertainment, healthcare, autonomous system, and Internet 4.0, or the challenges, or should I say, the research directions of many practical applications and deep learning, deep neural network models, your insight on each topic was truly captivating. The different approaches to enhance the neural model developed or address data related issues will truly inspire our students to work on such problems in the future. It was indeed an enlightening session. Thank you for sharing with us your valuable knowledge and time. Looking forward to having more such interactions with you, sir.
Thank you.
Thank
It
you.
was a pleasure. It was a pleasure to talk to you, talk to this forum and the students over here. Thank you.
Thank you. Thank you, dear participants. So please fill in the feedback form, and it's posted in the chat box for you guys. Thank you everyone for your active participation today. We will wind up for the day. Let us join virtually tomorrow at 9 a.m. for the keynote session by Dr. Vinod Patange, distinguished member of technical staff, senior member Wipro, to share with us his knowledge on features to embeddings, unified view of ML pipeline for text, audio, and image understanding. Thank you, students. Thank you, sir.
Thank you, Sunando. Would like to meet you in another forum. Yeah. Bye.
Thank you.
Take care.
Thank you. Bye.
Bye. Students, we have posted the feedback link in the chat box. Please enter your feedback and you can leave. Thank you.